Hello students, welcome back to chemistry class. Today I am here with another topic of chemistry. What is the topic? You know that this is very important topic for all of us. Here it is, what is that? That is behavior of gases. Behavior of gases, and other is, what is that? Van der Waal equation. What is Van der Waal equation? First time you are going to study here. So just this is Van der Waal equation here. And next is compressibility factor. Compressibility factor, Z equal PV upon RT, or Z equal V real upon V ideal. Other point is here, boil temperature. Boil temperature. You don't know? So to see this, you have to watch this video till the end. The Z value, what is Z value? What is the importance of Z here? We will see Z equal 1 for the ideal gases at all temperature and pressure. And here, when the behavior of ideal gas will be followed by real gases, means when real gases will behave as ideal gases, what is that? Where? Yes, this is it is given in this video. So when at high pressure, no, at low pressure and high temperature, the real gases show ideal behavior. Okay, so if you understood whatever is being taught by me, please like and subscribe my channel for more updates of chemistry topic. Okay. So now question arises, why do the real gases do not follow the gases law? Why do real gases do not follow gases law, and why do real gases shows deviation from ideal gas or gases law? What is the reason? What is the situation under which they show deviation? Under that they show deviation. So let us see here. If we search reason behind this, it has been found that the first two concepts of kinetic molecular theory is not hold good by the real gases. Means first two concepts of kinetic theory is not hold good by the real gases. So what were the concept? First concept was that there is no intermolecular force between the particles or between the gaseous particles. There is no intermolecular forces between the gaseous particles. Second was that the mass of gases were taken as point mass. Sorry, the volume of gases were taken as point mass. So in that concept, it was told that means there is no intermolecular forces between the gaseous particles, and the volume of gaseous particle is negligible than the container. Means here we have to remember two concepts were taken. What was that? First, no intermolecular force. No molecular force. Molecular force. Second is that volume of gases. Volume of gases. Volume of gases are negligible. Negligible means these two concepts are not being held good by real gases. These concepts are being held by ideal gases, but this concept is not being held by real gases. So what things required here? If we assume that there is intermolecular forces between the gaseous particles, in actual the real gases have intermolecular forces, and volume of the gases can't be taken as zero or as a point mass. Here other point is a point mass. Volume was taken as point mass. means negligible. Okay, so these on considering these two concepts, we need to correct in ideal gas equation. We need to two corrections in the ideal gas equation. What is that? First correction, that is what is correction in pressure, correction in pressure, and second correction in Waal. So if we are making two correction in ideal gas equation, PV equal nRT. Okay, if we are making two correction, these two corrections, so after that we get another equation like this: P plus a n square upon v square of v minus nv is equal to nRT. Okay, and this equation is known as van der Waal equation. This equation is known as van der Waal equation. Known as van der Waal equation. Okay, children. So let us see how do these corrections were made in the gaseous equation PV equal nRT. Okay, so let us see. So at high pressure, the real gas at high pressure interact with each other. Real gases at high pressure interact with each other. Okay, real gases at high pressure interact with each other because they are very close to each other. At high pressure, the real gases interact to each other because they are very close to each other at high pressure. At high pressure, the gas molecules do not, just all of listen here, at high pressure, if we see at high pressure, gaseous molecules will be closer. Gaseous molecules will be closer, like this only. So at high pressure, just see at high pressure, gas molecules do not strike to the walls of container with full impact because these are dragged back by other molecules due to intermolecular force. Due to intermolecular force. It means here due to intermolecular forces. And the pressure exerted by the gas molecules is lower than the pressure exerted by ideal gas molecules. Ideal gas molecules. Here. Okay. So let us see one more time here. What I told here, at high pressure, gaseous molecules interact with each other because they are very close to each other. At high pressure, the gaseous molecules do not strike to the walls of container at a higher speed. At high speed because the molecules are being dragged back by the previous molecule. Dragged by the, like this, just you see here, if it is striking, so if this molecule is attracting that, because in this we got idea, intermolecular means we got idea that the molecules interact each other. At higher pressure they are very close, and they are very close means intermolecular force acts between them. In this case, molecules do not strike to the walls of container at full impact, and the pressure is exerted by the gaseous molecules or by real gaseous molecules lesser than the pressure exerted by the ideal gas molecules. So in this, the ideal gas pressure exerted by the ideal gas will be equal to here P ideal equal is P real plus A n square upon V, where A is a constant, okay. And at high pressure, just sort of see, at high pressure the gaseous molecules are very closer. At higher pressure gaseous molecules are very closer. It means they acquire some space in container. It means the space available for the movement of gaseous molecules is like this. Here what we can write, V equal what is V minus NV. V minus NV. What I told, just sort of see what I told. At higher pressure gaseous molecules are very closer. Means they might be acquiring some space in a container. So volume available for movement of gaseous particle will be V minus NV, where N is number of molecules and V is a gaseous constant. When we put this value in this, so what equation we will get? One equation we will get, and that is known as van der Waal. So what equation we have already discussed here? PV equal nRT. What is PV equal nRT? So if we will put this value, equation we will get here P ideal plus P here. So P real plus N square upon V square. Here in place of this we will write this value, V minus NV is equal to nRT. Just sort of see here, nRT, and this one is known as van der Waal equation. This one is known as van der Waal equation. What is van der Waals equation. Okay, and here N is the number of molecules. A is gaseous constant, V is also gaseous constant, and A and V value depends on the nature of the gases. A and V value depends on the nature of gases. In this case, A measures the intermolecular force between the molecules, and it is independent of temperature and pressure. So let us see here, ideal gas, when we made two corrections, volume correction and pressure correction, we get this equation, P real plus A n square 1 V square, V minus NV equal RT. This is known as van der Waal equation. Where A and B are constant and its value depends on characteristic of gases, where N is number of moles here, and A shows intermolecular forces between the particles, and it is independent of temperature and pressure. Real gas show ideal behavior at low pressure and high temperature. This point here, real gas shows ideal behavior at low temperature and high pressure. Okay. Deviation from ideal gas, deviation from ideal behavior in term of compressibility factor means the deviation of ideal behavior. The deviation of ideal behavior of real gases means deviation from the ideal behavior of real gases is represented in term of compressibility factor means deviation from ideal behavior is denoted in term of compressibility factor, that is Z, means deviation is denoted in the form of Z, that is known as compressibility factor. Z equal PV upon nRT and Z equal 1 for ideal gases at all temperature and pressures. For ideal gases, the Z value is 1. The graph Z versus P is a straight line for ideal gases. But for real gases, Z value is not equal to 1. For real gases, Z value is not equal to 1. Z value is 1 at very low pressure, at very Z equal 1 at very low pressure. Real gases behave as ideal gas means if pressure is very low, in that case the real gas behave as ideal gas. In that case Z value is 1. So let us see here students, Z value is greater than 1. Z value is greater than 1 at high pressure. Okay, at intermediate pressure most gases have Z value more than 1. At intermediate pressure most of the gases have value more than 1. Gases shows ideal behavior when volume is very less. Gases shows ideal behavior when volume is very less. It means gases are taken in huge volume. Listen here, means if the volume occupied by the gases is very less in comparison to container in which they have been taken. Here, let's see. Gases show ideal behavior when volume occupied is very less than container. Is occupied very less than container. Here, boil temperature. Boil temperature. Let us see here. This is new point here. Boil temperature here. So what is boil temperature? Temperature at which a real gas obeys ideal gas law. Just also see. Temperature at which a real gas obeys ideal gas law over an appreciable range of pressure called boil temperature. Just listen here, means temperature at which a real gas follow or obeys ideal gas law over an appreciable range of pressure called boil temperature. Boil point or boil temperature, we can write boil point or boil temperature of gas depends upon its nature. It means it is different for each gas. Boil temperature is different for each gas. Other points, just also see here, boil temperature at this case Z is more than 1. Z is more than 1. And here above the boil point gases shows positive deviation. Above the boil point gases shows positive deviation and below the boil point gases shows negative deviation. Above the boil point gases show positive deviation and below the boil point or boil temperature gases shows negative deviation. So here what we got, that real gases shows ideal behavior at low pressure and high temperature. We were discussing about the boil temperature. So on increasing boil sorry on increasing pressure, the deviation decreases to minimum point. Here just listen, here boil temperature, okay, boil temperature we have seen here. So above the boil temperature, gases shows positive deviation. Below the boil temperature, gases shows negative deviation. So on increasing pressure, on increasing pressure, on increasing pressure, on increasing pressure, deviation decreases. Deviation decreases to minimum point, to minimum point, and further on increasing pressure, further on increasing pressure, it increases, it increases, further on increasing pressure, increasing pressure, it increases. What increases? The deviation increases. Okay, and here pressure increases and the value Z also increases, and in this case the value Z also increases. Means here all of us see here, means below the boil temperature, gases show negative deviation. On increasing pressure, their deviation decreases. Their deviation decreases at a minimum point, and further on increasing pressure, it start again increasing, and Z value also increases for that. Okay, and here if we see above explanation shows that at low temperature, just look here, above explanation what we have discussed before this shows that gases, means the real gases shows ideal behavior at low pressure and high temperature. Okay, other point if we see here, just all of us see here, if other point we see here, what we get. So let us see here, if we write here Z, we have already done that, PV equal nRT. So in this case, if we write here the Z value like this, it can be written PV real means P V real upon nRT. If the gas shows ideal behavior, then V ideal can be written like this. V ideal can be written like this. It means V ideal will be equal to like this. If we are converting this, it will be equal to like this. And when we put this value, putting this value in equation, if we put this value means V ideal value. So in place of this, what we can write? We can write V ideal, and Z equal is V real upon V ideal. On this basis we can say compressibility is the ratio of actual molar volume of gas to the molar volume of it. Means the compressibility is the ratio of volume of real gas and volume of ideal gas. Okay students, so today we have discussed all these points. I tried to explain it easily. If some problem is there, you can comment on my channel. If some doubts are there, you can comment on this. I will explain once more. And students, get ready for new updates of chemistry. Okay students, thank you so much.